computer. There you go.
Mm.
Yes. At 3, 2, 1. Hi guys,
Okay.
we are back with a new video today. So today we are starting a new series of episodes on our podcast. It's called Quantum Leap. So it's
Mm.
the episode number 1. So today we are talking about the double slit experiment and how we both have been fascinated by it for the
Fascinated.
longest time.
Yeah.
Yeah. So basically, even in school, we used to think about how does this happen, and all of that. We were always given a reason that yeah, that is how it is. Don't ask questions. And then
Mm.
now that we are a bit more free, we are looking into exactly how all of this is working. So we have referred to a lot of YouTube videos. We will link everything in the description. And basically, the whole point of talking about it is giving our perspective of what we
Yeah.
think about all of these, all these
And most of it is for our own benefit because we want to know how much we know about it.
yeah,
So
and
by discussing and by talking about the things that we learn throughout the uh, between the podcasts, we would like to share, and with that, it will help us also. So it also has a selfish motive, I think.
yeah, with that negative quote from Yash, as usual,
It's
we
not
can
negative.
we can get started. Okay, so Yash, what so people who are interested in physics know what the Young's double split experiment was. Okay, so can
Hmm.
you explain it in brief what it was like?
Okay. So Young did this experiment. It included a small slit that through which the light was going to pass, and there was a wall between the screen and the source of light, and in that wall, in the middle wall, there was going to be two small slits. So the size between the slits is roughly equal to the wavelength of the light. So he chose a monochromatic light. First, I think he chose a white light to traverse um, through two slits. So first he tried it with the white light, and when the light passed through the double slits, he saw a kind of pattern on the wall. Okay, so the pattern that was formed on the wall was not what you would expect. I mean, it was just a revelation that light can be a wave. So it behaves principally like a wave because when it travels through the two slits, it form an interference pattern. So what do you mean by interference pattern? So what you would think that it is what is intuitive that through the two slits, if any light passes, at the other end of it, you would see two like when you
Bands.
see a silhouette, yeah, two lines, two bands. But it was not like that. The first of all, the two slits were very tiny because the distance between the thickness of the slit was equal to the wavelength, as I stressed earlier, wavelength of the light. It roughly equal to that. So that was the defining factor in that experiment. So what you would expect was not what the result was. So the interference pattern included the between it formed an interference pattern of bands. Like the middle band was the brightest band. Then there was a slightly darker band. I mean, then after that, the dark band and a slightly bright band, less brighter band than the middle band. So we'll share the image. That will be much clearer.
Yeah, yeah.
Okay.
So, uh, So
Exactly.
basically, the experiment, what
This
he
was the
did.
experiment. Yeah.
Yeah, this was the experiment. So Thomas Young did this experiment in 1804.
Hmm.
1804, you have to imagine, it was before any subatomic particles were even discovered. Nobody knew anything about it. Okay,
Yes.
he just observed that and then started thinking, why does this happen? And then when
Yes.
he started thinking why this happens, he came to a conclusion that yeah, light, the only way. So yeah, we are used to see these ripples in water, right? Circular ripples in water.
Hmm.
So
Yes.
he saw that and he started thinking, okay, these are waves. And if you like have a barrier at the end of it, then
Hmm.
these will work. These will basically be again waves. Like these waves will form those bands, like dark and light bands, right? So he that is how he proved that it is a wave. The light has a wave like structure. Okay.
No, basically, see, okay. Uh, Let me just explain it in a brief. What was the conclusion behind the interference pattern? Okay. So when the light waves traverse through the slit, it when one, I mean, the source of light produced a single ripple, right? And after it was divided, uh, after the two slits were introduced between the source of the light and the screen, the single ripple of a light wave was converted into two small ripples. Okay, so when the two small ripples came together and they interacted with each other, I mean, they interfered with each other, it formed a interference pattern because um, at at the center, when the two waves were in phase. Okay, so by in phase we mean that the wave is a, I mean, it has a
Basically,
what we call,
the trough and the trough.
yeah, trough.
There are
And
two waves. The trough
yeah,
is the first
I was
one, and the
going it in much
second.
basic. Okay.
Yeah, both go in the on the same time. So basically, both get added.
Yes,
When there is
both get added.
when there's a dip,
So there was the
there's-
bright band.
yeah,
Yes, and similarly, when the two waves were out of phase, it formed a uh, dark band because the crest and trough cancelled each other out, and so there was no there was no light that was going to be formed at the screen. It cancelled each other out, the energy cancelled each other out, right?
yeah, yeah.
Okay,
So
so that was the basic principle.
this was what like Young did in like 1804. So you
Right.
have to think of. I'm pretty sure that even he did not know like a lot of things that he had actually done. So it was a incredible thing, and people still are wondering how is it possible. Okay,
Hmm.
that just goes to say that it is one of the most I don't know, one of the
Revolutionary,
biggest ex-
revolutionary experiments. Yes.
revolutionary experiment that he had come across. Okay,
Hmm.
so moving on, when you like think about Young and all of that, these so I hope by now the Young's double slit experiment is clear. Okay,
Hmm.
there were a couple of problems with Young's
Yeah, I just wanted to clear out that when the source of light was a white light, it formed. I mean, there was a diffraction concept also introduced in that because the light that was observed on the screen was had all the. I mean, it was a rainbow basically, not a rainbow. I want to say that it had all the colors. I mean, the white light was
dispersed.
dispersed. Yeah. Is
Yeah,
it diffraction? Am I right?
yeah. Basically, what happens when you see through a prism, like the white light passes through a
Prism.
prism,
Yeah.
you
Huh.
have diffraction. Right? That. Uh,
Hmm.
I think it is called dispersion. Diffraction is when
Dispersion,
the
yeah.
yeah
When the light bends on the corner, yeah,
yeah yeah,
right.
yeah.
That is diffraction. Hmm.
So, so yeah, there were a couple of problems in considering light to be just waves. Okay,
Hmm.
so the first problem was Max Planck introduced, like he came across all of these problems. So it was the radiation density emitted by the black body, which could not be
Hmm.
explained by this. So black body, so when you think about a black body, basically it attracts all the light.
Yes.
Okay, so it does not like radiate anything, but there is like 1% of radiation which happens, and
Hmm.
it was formulated by people before Max Planck, and this radiation did not, I don't know, follow what the Young's principle was,
Wave,
wa-
wave
wave
nature.
principle.
Okay.
Okay, and the second problem with this experiment was that the photoelectric effect that we see in,
Hmm.
let's say, solar. Solar is what photoelectric. So when a light falls on a metal, it disperses an electron out,
Hmm.
and basically it produces electricity. So light producing
Right.
electricity, photoelectricity.
Yes.
So that is how
So
the light.
that's why,
So
yeah.
how do you disperse one electron? If you are a wave, how will you disperse one electron? So you have to be a,
Hmm.
particle. So you have to be a marble so that you can come hit a marble and then you disperse that marble. So
Okay.
that is how like the photoelectric effect was also not explained.
Hmm.
So after that, after several years, like people, I don't know, scientists like Schrodinger, Heisenberg, and all of these people created this modern form of like quantum mechanics, which had
Which
light,
had both.
as both wave and particle, which they call wave particle duality.
Right.
Okay, so we are trying to go into the history of how this came about. Like, I don't want to
Hmm.
directly jump to yeah what it is now. Okay,
Right.
yeah. So uh, there were experiments going on like in the 1961. So I have this written down, and I would like to share this. The first double slit experiment with electrons indicated that an electron beam behaves as a wave, but since Johnson couldn't create a could not create or measure individual electrons, he couldn't prove
Yeah.
that each electron itself has a wave-like character. So that means
Right.
that there is a difference between a beam of electrons and the electron itself. So it's like a droplet.
True.
Okay, water has
Right.
droplets. Can you like, because water is just a wave, you cannot like isolate a droplet out of a wave. So
Yeah.
so it is a good analogy that I use to think about it. So to isolate one droplet, you have to think of what is the volume of the droplet. If you say, let's say, electron has its own energy level. Okay, if anything is that level, then it is an electron. Okay, so that
Hmm.
is how you can differentiate two electrons from each other. They have different charges. Okay, so
Okay.
in the 1961 they did not have any way of measuring all of this. So in the mid 2000s, using electron microscope, Farnboy and his team were able to reduce the beam current to such a low level that they could predict with a very high probability that no more than one electron was between the source and the detector. So this was a big
True.
revelation. Now in 2000s you
Yeah.
have
It allowed the experiment. Yeah. The
yeah.
it allowed the experiment that was envisioned before to be carried out
So whenever
later.
you are whenever you like think about like these experiments, so in the Young's experiment even, you think about one electron at a time. What happens if you send one electron at a time?
Yes.
You think about that and how it will work. And then so you need like material, like let's say sources, detectors that are that accurate, right? So
Yeah.
because there were no detectors and sources like that time, so they could not measure any of it. Okay.
Yeah.
So I'll take uh, let's say I'll take a lot of reference. I want to explain where it is right now, at least where I see it right now.
Just first explain. Can you explain the experiment which included the, I mean, a single photon will be emitted through the photon emitter or an electron, and when it will be passed through the double slits, and what will be observed at the end of the screen after emitting a single electron for a while. I mean, for a particular time period. After a time period, what will be observed on the screen?
Yeah, just a second.
Please explain the experiment.
Yeah, let me. I have a very interesting picture that just demonstrates this. Okay, this is taken from a YouTube video,
Hmm.
and let's see. Can I show this? Yeah. Mm, share. Yeah. So if I hope you can see this, right?
Yeah.
Can you see this?
Yes.
Yeah. So here you can see that this is the slit here,
Hmm.
and you are bombarding one electron at a time. Okay,
Yes.
and one so what you should ideally see is this two bands.
Yeah. That is the, yeah,
That is
that
that is
is
what
what
you should
you
ideally
think
see.
you would see.
Okay,
Yeah.
yeah, but but what happens is because uh, there is no detection of what kind of element or what this is, what electrons are. So what you
Hmm.
see is something like this. Let me share yet again.
Okay. Just in brief, I will explain this. Okay. So what happens is, uh, at first we experimented, um, uh, thinking that, I mean, assuming that light is a wave.
Yeah.
Okay.
So I think
So
you can
what we
see
observed
this.
on the screen, yeah, okay. See, this is what we experimented first. I mean, Thomas Young experimented. We didn't experiment, obviously. So uh, what we saw is the interference pattern. Okay. So now there is the particle nature of the light that we had, that was introduced by Einstein, and so we would think that what would happen if a particle is passed through the both slits, and what will be observed at the end of the screen. So as we thought, as the image explained earlier, that what we would think would happen is not what will happen. Okay. So by emitting a single photon or an electron through the photon emitter or an electron emitter, whatever, through the double slits at single time. I mean, one photon after another for a time period. And at the end of the experiment, what you would expect is not what you see. You would see the same interference pattern that we saw earlier with the help of, uh, I mean, when we took a monochromatic source of light. Okay. So it was very counterintuitive because it is not interacting with any other particles. It is passing single particle through the slit. So how would this happen? This is the dilemma, I think. Okay.
Yeah. Yeah. So
This
now
is the
in
dilemma.
the picture you can see that there are, so what happened was when people, so Yash explained it very well that this is the interference that you'll see. Okay, even
Hmm.
if you send particles, this is what you'll see. Okay, people
Right.
started wondering, is there any way in which we can detect which like which electron goes through which slit, like does it go through this or this?
Yeah.
So
Because
what
there is
is it?
nothing it was interfering with. So they
Yeah,
wanted to detect which from which slit it was going to pass.
yeah.
It is
So
passing through which slit. Yeah.
yeah, so
Continue.
what they
Continue.
did was they put something like this, that is a red and blue screen. So what it
Hmm.
did was it used to like the elements, the electrons that came through the right slit will become blue, and the elements and the electrons that came through the left one will become red.
Yeah.
Okay,
True. Okay.
so you'll see a rainbow-like thing was what was expected, but what you saw
Hmm.
was again two bands. So
Double slits. Yeah.
yeah,
Two bands, not the interference pattern.
yeah, just the two slits. So what
Hmm.
happened was we basically what was concluded was the coherence of the coherent source was broken. What does
Hmm.
coherence mean? Coherence is basically if you have a source that produces exact sine waves, that is there is no phase difference between two electrons, two waves.
Okay.
That is what coherence is. So
Hmm.
because this layer it created a phase difference, because blue color and red color created some kind of phase difference at the core.
Okay. Leave that. Okay. That's all. Okay. Even if we don't introduce the layer, okay, we take single sensors at both slits, okay, two sensors. Huh? So even if we are not introducing any phase difference or anything, we would still observe the double slits after measuring from which slit the photon was passing through. Okay, so this thing is called in quantum mechanics. It is called. Let me just refer it. Okay, so this thing is called the act of observation. Uh, I mean, in quantum mechanics, if anything is observed, it it doesn't. I mean, it collapses the wave function. Okay, so we'll explain the wave function later. Just to get clear what act of observation means. Okay, so whenever we introduce anything that we are observing and we are measuring, the act of act of measuring at the double slits. Okay, when we measure anything, it will produce different results in quantum mechanics. This
Yeah,
is called the act of observation.
yeah.
We don't know why. I mean,
So
there are interpretations. Yeah.
no, there are a couple of reasons why that happens, and it
Hmm.
is
There are
I read it.
exactly interpretations.
Yeah, that is so. Basically, what happens is what Yash is saying is, let's say we put a what is it called, observer here. Okay,
Hmm.
I think you can see the blue this thing, blue circle.
Yeah.
Can you see the blue circle?
Hmm.
Okay. So you see, like you are the observer, you are here, and you're trying to see through the first slit. You're trying to observe.
Yes.
Okay. So what happens when you're observing something is basically, so what happens in the experiment I'll explain is that
Hmm.
the coherence is broken because we are basically
What is
observing.
broken?
Coherence is broken yet again.
Okay. What is coherence?
Coherence is basically there is a phase difference between two electrons. If there is no phase
Hmm.
difference, if there's no phase difference, the band is created. The
I'm not able to understand
okay.
what electron and what phase difference.
So yeah, so you can see the waves here.
Hmm.
You can see the waves here, right? So these are in phase, right?
Yes. Okay.
Okay, these are in phase. But when you put an observer here, the coherence is broken. So how? how is that shown? Like, how do you know that the coherence is broken? Is that this pattern that you see is gone?
Hmm. But this is the wave particle, wave source, right? We
Yeah,
are
it is a
talking about the
coherence.
particle source.
No,
So there nothing happens when
exactly. This is the point. What I'm trying to make is that the
okay.
source is not. You cannot just distinguish between a particle and a. The source is the same. Okay, you're
Yeah,
sending.
source will be the same, right? Okay,
Okay,
obviously.
so you're sending. Let's say if you send, let's say only one wave of this, and let's call it
Hmm.
an electron. One wave of this source is an electron. So usually it's not like that, but let's say, okay, if we say one, this is an electron, then this can be a particle, I don't know, source too. Okay, but as this is sending in like continuously, that is why
Hmm.
it is a coherent source.
Mm, okay.
If there are two waves that are going, right? If the two
Hmm.
waves have no phase difference, then they are
Okay.
coherent sources.
Okay. Uh, I'm a little bit confused, but
Okay,
I think
so let's
okay.
get back to this and I'll explain it again. Okay, so let's consider.
Let just explain it through the perspective of when we introduce the particles that will be passed through the slits. Okay.
Let's go back.
Huh. So do you agree with me? Just let us get our opinions matched. Okay. Not opinions, the facts. Okay. So we just explained that the act of observation makes the uh, interference pattern disappear and the double slit pattern appear on the screen when the photons are fired through the
Yeah,
double slits. Okay.
yeah,
So when we say that the act of observation or act of measuring, we talk about the sensors or detectors that are placed at individual slits, okay, without disturbing the experiment. You understand?
yeah,
Without disturbing anything. We are just measuring. Okay.
yeah.
So yeah.
So
Um,
basically, there are interpretations of why this happens. That whenever you observe
hmm,
something, why does it go out? Why does it change state? Okay, so
yeah.
I saw this great explanation given by Neil deGrasse Tyson, and I
Hmm,
really
hmm,
think it is right. Like it makes sense to me.
okay.
Okay, so let's say I have a cat. Okay, and
Yeah.
I'm looking at that cat. So it's in my room. So I'm looking at that
Hmm,
cat. What does that mean? Is that light is falling on that cat and then reflecting into my eye. Correct.
yeah.
So now let's make that cat quantum. That is it. The weight of the cat is as much as an electron or a photon.
Hmm,
The charge is nil. Okay. So
hmm,
now the room is dark. I don't know where the cat is. Okay. But
okay.
the moment I want to observe that cat, I turn on the light.
Hmm,
Okay. Once I turn on the
yeah.
light, what happens is photons from the light source go and fall on the cat and then they reflect back to me. Right.
Hmm,
So now as the cat is so small that
hmm,
that the moment the photon bounces on the cat's surface, the cat gets
hmm.
displaced.
What do you
So,
mean displaced?
so like a marble, the photon comes, hits,
Okay. Ha,
and then
right, right. Okay.
it gets displaced, and then
Ha,
the photon comes and comes into our eye. Okay,
ha.
that is why the information that is sent from the photon. So we are expecting the cat to be there, but it is not there because it has been displaced by this
Displaced.
photon itself.
Okay.
Okay,
Okay.
this is why there is this confusion. So anytime there is information change, information
Hmm,
there is if you get some information out of anything, there is a
hmm.
change in state of that thing. This is what it proves.
Okay.
Okay.
Okay. Fine. Okay. Okay, I understand that. Okay. So without changing the particle, okay, when we observe the experiment, you say that um, it will display the interference pattern, right?
Yeah,
Without changing
without
anything.
observing. Yeah.
Okay. So so while we are observing, we are changing something. And you say that while we are observing, we displace, I mean, what do we displace exactly?
We
What
displace
changes
the
are
actual
introduced into the,
the particle that you're looking at. That's what the cat. Okay, you're displacing the cat itself. So whenever you're displacing the cat, the light particle that hits the cat and comes to me is saying the information that it is containing is that the distance is here. So the distance is, let's say, 10 meters.
talk it about the in the context of this experiment only, please.
Okay, so let's say, I think you can see the screen, right?
Hmm.
So let's say you have an I'll try to draw. Okay. Yeah. You have an observer here.
Hmm.
Okay. Let's not have observer there. Let's have an observer here. Okay. You see this
Okay.
observer now? It is looking directly at this. Okay.
Huh.
At this photon. So when this photon
Yeah.
goes through here,
Hmm.
goes through here, what
Hmm. Hmm.
happens is what happens is there is some so what happens when you're observing that this there is there is, let's say, light coming here and then getting here, right, into the observer. When you're observing it,
Okay.
what is happening is the observation that is made is not made blindly. It is made uh, by the communication of something, by communication of information. The information is carried by the light, correct?
Okay. Okay.
So whenever this light comes, and if the weight is big enough, then the observations make sense. Okay, but as the weight of the particle is so less, so minute, that
Hmm.
this
Hmm.
this particle gets deviated here. So the new particle is here because we are observing that.
Okay.
So this goes and crashes into here, and it is done. So every time you observe, the coherence is broken.
Okay. But how does it conclude that uh, by observing, I mean, first of all, there is the dilemma that why does it produce the interference pattern? Even if the single photons are fired, what does it interact with?
Yeah,
Okay, that we don't know. So
yeah, we
to
don't.
correct, to correct that, we introduce this experiment of a detector, right? To understand where the particle is and where it is, I mean, what it is interacting with to produce the interference pattern, right?
That
Okay,
is why
you
we are
said,
observing.
okay, you said, I think I can make sense of that. But so you talked about an observation, right? So what if we introduce a detector instead of an observation? I mean,
So
instead
yeah,
of an
go ahead,
observer.
go ahead, go ahead.
Okay. So the detector, what do I mean by detector is it will, or a sensor basically. Okay. So it will, so when the photon will be passed through the slit, okay, the other side of the slit, there will be so first let me explain the concept of quantum entanglement. Okay. Basically,
Wait,
quantum entang
let's not get into quantum entanglement because it is a huge
just
topic.
briefly. Yeah, no, brief.
Let's okay.
See, okay. Simple, very simple. Any particle that is same with matches the properties of another particle are said, those two particles are said to be in quantum entanglement, right? Okay. So both particles have same properties. Okay. So what we do is when the particle will be passed through the single slit, I mean individual two slits, at the other end there will be a mirror or lens, that will that will I mean divide the particles energy
We'll
into
get to that.
half.
We'll get to that. We'll get to
Okay,
that.
we'll get to that.
Yeah.
Fine.
So
I just
let's.
wanted to say, okay, fine. You
I have an
continue.
image for that, and I think you'll be able to explain it better from that.
Okay, fine.
Okay.
Okay.
So this is how this is what happens whenever an electron whenever you try to observe an electron, okay, individual electron,
Hmm.
and even if you have a sensor, even if you have an observer, not an
Hmm.
observer, just a sensor, just something that makes an observation, okay,
Hmm.
the observation is made only when there is some transfer of information from the particle to the observing this thing sensor, right?
Yeah.
So let's consider LDR. We know LDRs, right? Light dependent resistance.
Hmm.
So the information that the right light LDR is getting is the light intensity.
Yeah.
Do you get it? Okay. Similarly, here the information that is traveling between the information does not have to be in bits. It does not have to be 1 0. It can be intensity. It can be anything. Okay.
Okay.
So the information that is being transferred from the particle to the to the observer.
Hmm.
The only way you can make observations is uh, if you observe an element. And what does observe mean? You look at, like, you collect information. Correct?
Yeah, I understand. Okay,
Yeah.
that's why I was explaining the lens thing.
Yeah. So let's go ahead.
Okay.
So that is why so this information transfer causes a problem uh, in the observations, and we have to consider that, is what I feel. Okay. So this is the double slits experiment that was
Yeah,
taken.
this is way complicated, way more complicated. Just we'll get to this. This is the next stage, I think. The next stage. First,
Wait, let me
uh,
explain this. Let me explain this. Then you can explain
Pranjal,
this
but
part.
this
You
will
can
be
explain.
this is the last thing that we'll be talking about, right?
Okay.
Because yeah, this is the what we say quantum eraser experiment, a quantum eraser phenomenon, what we call. Okay, fine. First, just get to the I mean I mean the slits and the lens experiment. Do you have that image or? Okay,
Um,
let me find it. One second, one second. I was watching this guy's video called he's called Joe Scott. He explains very complicated concepts very uh,
like
I
us.
mean intricate, like very easily. I mean I don't know how he does that. Does that? One second. So let me find that image. Okay, yeah, this is the one. Let me just. Yeah, just a second. Paint. Opening the image. Okay. You can sketch in the Photos app, right?
You have to share your screen first.
Yeah, one second. Okay, I'm sharing the screen. Fine. Enable the screen sharing, please, Pranjal.
I think you are the host.
No, you're the host.
Yeah. Okay, there can be only one host. Okay. I don't know
Yeah.
that.
Okay, fine. This is the slit. I mean, this will be the mirror or what we call a lens.
No, it is a
Okay,
crystal.
crystal, yeah.
It is a crystal that divides one electron into exactly two electrons. So how do they know that it is exactly two electrons? Is that the electron charge, like the two electrons that are created, have the exact same charge, and they just have opposite spins. That is why they are quantum
Yeah, entangled. Okay, so it will each have 50% energy. So as we know that a single photon carries a packet of energy. So 50% will be divided into this better color. Undo. Damn it.
eraser. The fourth one is the eraser. The fourth one is the S.
Okay,
There you
red. Red is better. Okay, fine. This is the crystal. So it will divide photons into two um, opposite spins, right? I mean, it will introduce quantum entanglement. So both of these and this photons, this and this, will have same properties, right? Okay,
go.
so when any photon will be passed through through this slit, it will be divided. One will go to the screen and another will go to the detector or a sensor A. Okay, so we'll be able to measure the path of the electron or a photon that will be traveled through that particular slit. Okay, so in this way we'll be concluding the experiment. We'll be carrying out the experiment. Okay, so when this was observed, we still found that there was no interference pattern at the screen. There were just two bands that were observed without any interference. Even if we I mean, without any interference to that particle, we were able to measure that particle from which slit it came, even though even though we didn't interfere with anything, there was no interference pattern. So what can be the interpretation of that? What do you think?
That's what. So I don't know exactly why this is, and I've been thinking that, but the next experiment that they did was the distance between AB, like the
Hmm.
distance from the crystal of AB, they increased it to two times the distance between the crystal and the screen, so that the
Yeah, correct.
electrons
So that
fall
it will
on
hit
the
the
screen
screen
first,
first. Yeah,
and
correct.
then this they go to the detector.
Yeah.
Okay, but my question is, let's say you have like a huge, I don't know, a long, uh, the distance is a lot
Yeah.
uh, from the detector.
So
So
it doesn't matter, right? Where the where the photon is going after it bombarded on screen. Okay. So after it was after it landed on the screen, where does the another I mean the another photon go? It doesn't matter.
no,
But
it does
the
exactly. There is some kind of information that is transferred
yeah, yeah,
between
we
the
know
two
that.
electrons.
I mean we don't know that exactly, but we have some interpretations why
Yeah,
this happens. Okay. So basically what we were talking about is the um, the I mean the phenomenon in the future affects the past. I mean it's like saying that I mean the effect determines the cause. You understand? So
yeah.
take any analogy. For
I
example, yeah, do we need an analogy?
no, we
Don't
don't.
think so.
We don't. So,
We don't. Very bad at it. Okay.
so that is what.
So this is the crazy mind-boggling thing. Yeah.
Yeah, basically, before the electron lands on the screen, the electron already knows if
Hmm.
we are detecting the other its twin. Let's call it the twin. If we are detecting its
Hmm.
twin or not, and which is very weird, right?
Yeah. Very weird.
So That is what. So this is where my caveat comes in. That what if uh, we take like a long time to like we keep on reflecting the electron multiple times.
Hmm.
Let's say we give it 3 hours or something like that,
Yeah. Hmm.
and then we'll definitely be able to contemplate what is going on the screen, right? On the
Hmm.
screen. Okay, as we have not still observed like like the, let's call it A and B. The first
Hmm.
A twin will be on the screen, B will be like in the detector. Okay, we don't place the detector
Just
directly.
call it one and just call it 1 and 2 because we called the slits A and B, right? So detectors A and B. Yeah. So
Yeah,
we'll get confused.
let's say
Twin 1 and twin 2 or T1 and T2. Okay, fine.
yeah, T1 and T2. So
Yeah,
T1
that's smart.
T1 is on the screen. Okay,
Yeah.
and T2 goes to detector A, let's say.
Huh.
Okay, so what I'm saying is you don't put a detector there. What you do
Hmm.
is a bunch of mirrors, and it will just keep on reflecting, tap 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 tap. It will keep on reflecting for, let's say,
Hmm.
1 hour, some long time. Not, it does not have to be 1 hour. Maybe
Okay.
as long as our brain takes to contemplate what it is on the screen, what we are seeing on the
Hmm.
screen. Okay, once we make an observation about that,
Hmm.
then what we do is
Observation about what?
about what is on the screen. So
Okay.
either we see, so we should ideally see the bands, correct? We should see
Yeah,
the
interference pattern. Or
interference bands on the screen because we have not observed T2. Do you get it?
okay, yeah. Yeah, true.
Yeah. So we have
So
not
do we
observed
see that?
T2. Huh?
Hmm. Do we see the bands?
Yeah, that's so. So I'll explain the quantum eraser, then it will be like
Yeah, explain that.
I'll
Yeah,
get
fine.
to that. Okay,
I
let's
have not exactly understood that experiment. You will explain it better, I think.
yeah. So make me the host.
Yeah. Hmm. Okay. Done.
Yeah. This is the quantum eraser experiment, and it is the coolest thing I have read in the last, I don't know, 2 years.
Yeah.
So I'll try my best to explain the best I can.
Okay. Okay, just quickly. This is the thing that solved the I mean, this is what was done to get the interference pattern when the laser was introduced. Okay. Other experiments did not work. This experiment worked by measuring the, I mean, by measuring from which slit the electron was passed
No,
and
no. So
then
it did not.
concluding.
It did not make these observations. What it did was, it just
Hmm.
brought back the interference. I'll give you an example. I'll tell you.
Okay,
Okay.
fine, fine.
So this is slit A, uh,
Yes.
and this is slit B. Okay. This
Hmm.
is the crystal that Yash talked about,
Crystal.
which
Yeah.
divides everything in half. Okay.
Hmm.
So this is half of T1. Okay. And this
Yeah.
green one is T2.
Yeah.
So what came in was T from A. What came in was T. Then it got divided
Yeah.
into T1 and T2. Okay.
T2. Yeah.
Both are half in power. Okay.
Energy.
So
Just say energy.
energy. Okay. So what I'm saying is,
50% energy.
yeah,
Hmm.
50% energy. So what happened was, what they did was they connected two detectors here. Okay. And these are just
Yeah.
mirrors. They don't do anything. They are just mirrors. Okay.
They are mirrors and they reflect 50% and they absorb. They reflect 50% and they let 50% pass through. Yeah.
they they reflect at, they are reflected 90 degrees. Okay, so now what
Yeah,
happens
but they
is
also pass through.
50%. Yeah, so here
Hmm.
you see t t4 is 1/4 now. Here 1/4 of t4 is here.
Hmm.
Correct?
Hmm.
So I'll make it a bit more saner.
I just have a question. Okay. So, does the mirror do the job of a crystal, or does it
No,
just?
no, it does not. Crystal
So, how can you
allows
say that it's
everything that
one pore?
goes into it outside. So it does not have anything. It does not reflect. It just
Okay, it
refracts.
just refracts. Okay, fine.
Okay, and so what happens here is when the electron T2 comes in, A
Hmm.
detects it. Okay, A and B detect the T1, and let's say this is W1. This is W.
Hmm. Hmm.
This thing. Okay, W1 D W2. A detects T1, A detects T2, and
Hmm.
interference pattern is formed here. Okay,
Yeah.
so the caveat here is whenever the observers A and B, like the observation centers, what is it called? Sensors,
Detectors or
detectors.
sensors.
Detectors
Yeah.
are connected, and they're actually actively detecting. That
Hmm.
time, this is not like the pattern does not exist. But the moment you power this off, A and B, literally power it
Hmm.
off,
Hmm.
you
Hmm.
see the pattern again. It's so crazy. How is it possible?
Yeah, it's
How does
crazy.
it
Yeah.
how does it know that we have done that? Okay, then
Yeah, exactly.
secondly, to combat this, what they did was uh, what they did was, so this is the pattern they saw. Okay, whenever these
Hmm.
detectors were on, this is the pattern they saw. it it is nothing.
Hmm.
Okay,
Hmm.
so the moment this was turned off, this is the
Yeah.
pattern they saw. So
Great.
it was mind boggling. So just to take it a step further, what the physicists did was they connected two detectors here,
Two more
the same
detectors. Yeah.
two more detectors here, but what they did was they mixed everything. So basically they
Yeah. Okay.
mixed everything, and they made sure that the observations were not made. Okay, the detectors
Hmm.
are on now, they're not powered off, they're on.
Which two
And
detectors? C and D, right?
yeah, CND, but they're not making any observations.
They are not making observations. Yeah.
Then too, you saw this pattern. The moment
Yeah,
you,
you see the interference pattern when you're not measuring anything. That's the crazy part.
yeah, and I just my head was blown. How does it
Yeah.
know? Is the question. Okay,
What do you know? Yeah. Okay. Fine. Continue. Well,
okay.
finish
So
your explanation. Yeah.
this is what happens when you like this concept of erasing the information that was received from these
Yeah.
two this thing electrons is called um,
Quantum eraser.
quantum eraser. Okay, so there are two things. Okay, I want to, if I was a physicist, I would think about it. Okay,
Hmm.
so the first thing is, I'm sorry. Um, so the first thing is, what if I increase the length here? What if I make it long enough that my eyes are able to contemplate what is going on the screen? My brain is able to contemplate, because all of this happens within like 10 nanoseconds or something like that, something crazy. Okay,
Okay.
our brain cannot understand that at all, because
Hmm.
it's all happening at speed of light. Okay,
Hmm.
what I'm saying is, what if we extend it long enough? How can you extend it long enough is basically put a lot of mirrors, so it can just keep on reflecting, tap 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 tap. Okay,
Okay.
and then eventually when you want it to like you want to see like observe it, so
Hmm.
what you do is step one, increase the length. Okay, step two, and you like start the experiment, laser is on, you either see the these things, these bands, or you don't. Okay,
Hmm.
make that observation. You see these bands or you don't. Okay, then you remove the mirror that was holding this together.
Okay.
Do you get it? So
Little bit.
how do you increase this length? Is my idea is, you connect these something, let's say, I'll
But before that, just I think they were able to measure the. I
so
mean,
let's
they
say
were
the light
able
comes
to.
in here. Just a second. The light comes in
Okay,
here,
fine.
and you have a mirror here, okay,
Hmm.
and a mirror
Hmm.
here, and a mirror here, and then a
Okay.
mirror here. So you basically capture the light. Okay, it comes here, it bounces here, comes here, and then just stays here.
Hmm. Hmm.
And then you make this thing slidable, this this part, so that
Okay.
whenever you want, you can move this, and you have a detector here. Okay, the light
Okay.
directly goes into this. Okay,
Hmm.
this
Hmm.
setup is connected here.
Hmm. Hmm.
Okay, so what happens is the length is increased. So whenever the light is bouncing back and forth in this shit, we can make this observation. Okay, what are we seeing on the screen?
Observation how?
Or by our eyes.
Yeah. Okay. Fine. Yeah.
Okay,
By our eyes. Fine.
we either see something on the screen. So either we see the pattern or we don't see the pattern. Okay, there are two possibilities.
Wait. Wait. You are saying that you will see the interference pattern in this. I mean, the detector that you just drew. You're saying that.
No. This is for
Then.
T2. It's not for T1. T1 is here. It goes here. T2 is here.
Hmm.
Okay. So this
Yeah. True.
T1 will create some pattern here, right?
Yeah.
So as we are not observing anything, it should create this pattern.
Huh.
Correct?
Okay. Okay.
So once you see this pattern, then what you do is you move this mirror out of the way so that the light comes in and you detect the light.
Yeah. Fine.
Okay, then what happens to this? So now you have made the observation here, and then you're making the
Hmm.
next observation here.
Yeah. It will show the two bands because we have observed. We
No,
have
how will
made the
it show?
observation
We have already made the observation here.
because we explained it. I explained it in the previous experiment that even if you uh, increase the distance between the, I mean, first you let the interference pattern be formed, or let not the pattern be formed. First you let the two photons, first you let the photons be, I mean, displayed on the screen, I mean, to fall on the screen, and then you measure the, I mean, the dispersed, diffracted, not diffracted, um, the two that are divided into two particles, right?
Yeah,
The second one you measure it after getting the result on the screen. So even then, if you do that, you don't see the interference pattern. You just see the two bands because we
that's
have
what
measured it.
I'm telling you. What you said plus the quantum eraser. Okay,
Yeah,
this
they are successfully able to measure, I think, because when they when they lost the information, the A and B detectors here that you just, I mean, they are faded out right now. It was able to measure. I'm not sure about this because I didn't see this video, but I think they were able to measure the measure from where the photon actually came
no,
from, which
that
slit
is
the
the whole
photon.
question, right? That is the whole question. We are not able to measure still. Still till today, we are not able to measure. This video is around 4 years
Okay,
old. We are not able to
okay. So
understand
we are not able to measure from which slit the photon is coming at all.
at all.
So what is the purpose of this experiment? I don't get it.
That's what. So when you try to observe from where the electron is coming, you get the
Hmm.
pattern. You don't get the pattern. But when you don't
Yeah,
observe, you get the pattern. So how do you know? How does the electron know that we are observing it or not? What is the information that is communicated between two things?
yeah, true.
So
So what
this,
does the C and D detector do exactly?
so C and D,
What is their purpose? it is not observing anything, right?
No, they're just there so that they make an observation when it is needed. So they don't. So when the eraser is off, okay,
Yeah. Huh.
eraser is off. What does that mean? Is C and D is detecting.
Yeah, C and G is detecting and A and B is off. Okay.
Off. Okay, C and D is detecting. What is it detecting? It is detecting chaos.
Both of them. Yeah,
It's
both
not.
of them.
There is. You cannot figure out what is what because everything is
Yeah.
mixed.
Yeah, exactly.
That is when. So what is understood that you are detecting some light. There is something there, but you cannot understand what is there.
You cannot conclude. Yeah.
What is
When
there?
you go to make a conclusion, you lose the bands.
Yeah, you
I mean
lose
the
the
pattern.
yeah. So
Yeah, but how?
exactly, that is the
That's the
question.
point.
So my theory behind all of this is there is some information that is traveled. So the
Yeah.
information to understand in what dimension it is traveling. So there has to be another
Mm.
dimension through which it is traveling, which makes sense in
Yeah.
that dimension. Is what I'm
Yeah,
thinking.
there are exactly. Now we come to the last part of the podcast, I think. There are several interpretations why this happens. Okay.
Yeah.
So this principle that we have just observed is known as the collapse of the wave function. Okay. So do we want to get into the details of wave function or not?
No, no.
Okay, fine. Just we'll say that there is a wave function that determines the superposition of the two waves that produces the interference pattern, right? Okay, so what is collapsing of the wave function is that let me just refer to the Wikipedia page so I don't go wrong. Okay, so in the quantum mechanics, wave function collapse occurs when a wave function inertially in superposition of several eigenstates reduces to a single eigenstate due to the interaction of the with the external world. This interaction is called as observation. Okay, so it is the essence of measurement in quantum mechanics, which connects the wave function with classical observables like position and moment. Okay, fine. This is the basic thing. Okay, so this is the wave function collapsing of a wave function. That is, when the observation is made, wave function collapses. So the interpretations, there are, I think I've read about two interpretations. There are several of them. First one is the Copenhagen interpretation, which was made by Niels Bohr, and I think the other scientist was Heisenberg. I think
Yeah.
Heisenberg and yeah, let me just make sure. Copenhagen interpretation. Um, just a minute. Yeah, Bohr and Heisenberg, right? So they said, do you know about this, or should we just leave it to that?
I don't know.
I don't.
We will
Okay,
post something
I'll
in
just
the description.
I'll just say what I understand, basics. So I this is particularly my uh, understanding. So it will be definitely not the right thing. So should I continue or should I leave it to that? You just
Let's just give a summary in 1 minute
okay.
and then we'll.
Just a small summary. Okay, fine. So what I understand is that there is a probability of um, the particle that will be observed on the screen. Okay, so the maximum probability that we find the photon to be in the position on which the maximum probability of a photon to be appeared on that uh, interference screen is where we see the brightest bands. Okay,
Yeah.
so that's all I understand about it. I won't get into the specifics because I'm really not sure. I want to study it more,
Yeah.
and there is a lot of things that we need to
Okay.
study
Let's
to
let's let's
understand this.
let's get to like the two things that I am thinking. First thing is what if we increase the distance? That is the
Hmm.
first thing. So what if we make it as long as maybe like the length of the Earth? So are
Okay.
they still connected? Are they
Eh,
quantum entangled? That is the first thing.
hmm,
Second thing is, what is the information that is I don't know, what is the information that is conveyed between the two? How can you observe that? That is the question that you should think about.
yeah,
So
yeah,
the easiest way is, let's say, I see how detectors work, and maybe I can understand something more about that. So I'll do some research about this, and
yeah,
let's see.
fine.
Okay. Anyways,
Okay, do
I
you know
think
about the many worlds interpretation?
no, not really. I think we
Okay,
can
fine.
add that
We
to the
won't
next
get into that.
next.
Okay, we'll do it in the next podcast. Fine.
Yeah. Okay. It
We'll
was
schedule
it was a long. I know it was a tedious podcast.
educational.
It was yeah. Let's see. It was nice to get our thoughts out of it. Anyways, we'll see you guys next time, and till then, bye bye.
Yes. Okay.